Can I use the clicker? Does it work?
Yeah.
Oh. Okay, so I'll get started. I think a lot of the content that I have has some overlap with what Tom talked about in the previous talk, but I think it's packaged in a very different way. So maybe you can hear and tell me what you think. Okay, so I'll start. So imagine kind of a stereotypical image of a human interacting with AI. At least in my head and in a lot of media depictions, this is what it might look like. They interact and communicate with, they interact and communicate through natural language. And this used to be perceived as mostly aspirational until even like a few years ago, but using natural language to interface with AI systems has definitely become easier and more mainstream in the past few years. So for example, personally, I started asking more questions in natural language to AI systems, which I haven't been doing before and don't think was actually possible. So for example, I'll very colloquially ask how to solve my LaTeX problems. How do you make each line shorter in a LaTeX table? And the AI system also kind of packages its answers in natural language. There are a couple of ways to control the length, blah, 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 and goes on to provide its answers. So this kind of packaging also is often used even when the nature of the problem the models are asked to solve is actually non-linguistic. And as you can see, the reasoning behind the solution to the arithmetic problem, 3 plus 10 times 3, is being explained in natural language, multiply the numbers, add the numbers, and answer. And this kind of, yeah, that's what I just said. And there are two kinds of distinct capacities being recruited in successfully carrying out this kind of interaction. So there is ability to solve the non-linguistic problem at hand and the ability to provide adequate responses in natural language. And the latter capacity is constantly needed for almost everything that the model needs to do, while the former might kind of change depending on the nature of the problem. So the point is that the capacity to use, communicate with, and also reason in natural language is at the core of current and likely also future systems. Obviously, the caveat here is that I've made the motivation overly kind of tailored to chatbot type models for like easy exposition, but some version of statement I think would hold up for most like natural language text trained language models. So then how do we know if this core capacity is reliable? So I'll briefly introduce the idea of unit tests mostly as an analogy to the answer to the question that I just posed. And unit tests are small focused tests that are designed to verify expected system behavior. For example, I have a function called add here that should carry out addition, and unit tests help verify this add function behaves in the way that it should. And this is done by defining various test cases in advance where we know what the target behavior looks like. And importantly, each of these tests should represent a target abstraction. Here, I'm defining a test for cases where the operands are just positive numbers, and another test for cases where the operands are like, one is positive, one is negative. And are these good abstractions for the add function? It's questionable, but they are one. And the abstractions then are instantiated by concrete test cases. So I have 2 instantiations for each, but you're free to define many more. And the individual test case instantiations also should define the target behavior, which will be compared against the function's actual output to determine whether the tests pass. And you can see here that what goes inside the function definition body actually doesn't really matter. You might have no knowledge of what's going on inside here and still write unit tests, given that you have some conceptual understanding of what add should be doing. So this can be a black box. So working off of this kind of unit test analogy, we can imagine building a series of linguistic tests that we can expect the model with a command of language to pass in order to answer the question that I posed earlier, how do we know if the core language capacity of our models is reliable? So I have like a schema here where like the model is a black box and you define a bunch of linguistic tests where you define the target behavior. And of course, there are lots of questions we need to be asking here to define these tests. And namely, first, what are relevant and helpful units or abstractions? What are good sets of test cases or instantiations? And what should the target behavior be? And these are exactly questions that can be productively informed by linguistics and cognitive science. So for defining the units, we can draw from the subdisciplines, core concepts and phenomena, and finding good instantiations can be informed by experiment and stimuli design. And defining the target behavior can be informed by theoretical predictions and empirical observations in these fields. And kind of an aside, the linguistic unit tests we build will only be as good as our abstractions are, which means that the study of language itself and developing these kind of tests should progress hand in hand. So I've said this, then we build such tests, then what insights do they offer us, especially in terms of informing AI development? So one value, I think, comes from the fact that linguistic tests offer a fundamentally different carving of the problem space to downstream task-driven tests. So let's say that this is the space of problems that we want AI to solve. And this space might be occupied by various application-oriented tasks like information-seeking QA, machine translation, text-to-image generation, summarization, etc. And task-specific benchmarks are samples from each set. But if we look at problems in terms of the linguistic phenomena they contain or concern, the distribution of these kind of problems will cross-cut the boundary of the downstream tasks as indicated by these red areas. Can you see the areas? Yes. And this is important to note because the failure on the target linguistic phenomenon will be observed in practice across many different downstream tasks, but the root cause of the issue might not be salient or noticeable in task-specific benchmarks. And in particular, if there is no overlap between the red and the dotted areas, failures on the red phenomenon will be systematically overlooked by your task-specific benchmarks. So this tells us that failures diagnosed with linguistic unit tests have implications cross-cutting a wide range of downstream tasks. So one well-known example of this is negation. So for example, in text-to-image tasks, when there is a request to not generate something, models tend to generate them. So create images of a jungle with no river in watercolor style. There are rivers in all of the model generations. So that's bad. And we can also observe similar failures in instruction following when there is a negated request. So give me a list of top 10 US states by population, don't include the ranking numbers. And then the model still has them. This is an actual interaction that I had. So these are all real examples, anonymized to keep the model's privacy. And you can see that negation is an issue across multiple downstream tasks. And this is not just specific to a single downstream task of interest. And I want to quickly comment that going back to this diagram, at the intersection of individual tasks and linguistic units are also useful, especially in the context of critical applications. So I have personally looked into the case of false presuppositions in my prior work, especially this area in particular. So the intersection of false presuppositions and information-seeking QA. So the series of work I was involved in the past few years looked at questions similar in nature to the following. So for example, questions like, when did the fourth president of Korea get assassinated? So this question contains a false presupposition because the fourth president of Korea didn't get assassinated. Then an ideal model should be able to exhibit at least two types of ability to handle this question correctly. So one is sensitivity to the presupposed content, and second is to actually produce an appropriate response that challenges the false presupposition. There is also kind of like factual knowledge slash verification part here, but since this is not linguistic in nature, I didn't list it. But when subjected to these kinds of questions, we find that models often tend to accommodate the false presupposition. So here, the model I tested responded, the fourth president of South Korea, Park Chung-hee, was assassinated, blah, 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 where the mentioned president was indeed assassinated, but he is not the fourth president under any kind of ways of counting. So I like this line of work because it's intuitive to practitioners that these tests matter. So false premises started appearing as a category in QA benchmarks developed by some companies. And I do like to think that our work had some influence over this change. I have communicated to the authors. So moving on, what kinds of developments can failures on these tests, we build inform. So we just saw some failures. What kinds of developments can they inform? So intuitively, test failures inform solutions. And I group these solutions in terms of sort of synchronic and diachronic solutions. These are my labels. They're not like accepted terminology, I don't think. But I think both solutions are important. So I label solutions that are patchy, quick solutions that don't substantially alter the base model synchronic, and they can be informed by individual failures, and synchronic solutions are very important for kind of quickly patching up application critical mistakes. And the solutions that I label diachronic involve kind of fundamental, bigger changes to the base model / the general approach. And these are maybe more slow changes and are typically informed by accumulating converging evidence from multiple failures. So because this is a little abstract, I'll illustrate with 2 examples from my own work. So the first example is about tests for compositional generalization that we built a couple of years back with additional test cases released last year as well. So these tests are motivated by linguistic compositionality, composing smaller known parts to build up larger, possibly never observed expressions. And this is a key feature of linguistic competence. And in the interest of time, I'll discuss one example from a much larger test suite for compositional generalization, which is recursive depth extrapolation. So the ability or the unit tested here is that having seen only up to n depths of recursive structures, can models generalize to n+1 and beyond? So to provide an example here, given that you know how to map expressions like Ava saw a ball in a bowl on the table that has 2 embedded prepositional phrases to its corresponding logical forms or any kind of meaning representation that you like, can you also map expressions like Ava saw a ball in a bowl on the table on the floor that has 3 embedded prepositional phrases? And you can see that this kind of problem of recursive depth extrapolation requires handling of structurally novel expressions. And based on a meta-analysis of evaluations conducted using our test since it was proposed, this kind of generalization involving novel structures seems challenging for many different models, including very large pre-trained ones, which I don't find extremely surprising. And when grouping the type of solutions proposed into whether the solutions incorporate some sort of structural scaffolding, whether it be in terms of architecture, algorithm, or creation of supplementary data, we can see that any kind of non-trivial performance on generalization involving novel linguistic structures is only achieved by approaches that incorporate structural scaffolding, which is coded in green, as opposed to the purple ones. And one example of a synchronic solution is offered by Drozdov et al., who proposed parsing with prompting. So their structural scaffolding comes from a quite intricate design of the prompting pipeline that involves multiple steps of linguistic analysis. And here, each pipeline step is an LLM call with designed prompts / examples. And you can see here that quite a bit of prior knowledge about linguistic structure has been incorporated into the design. And what about diachronic solutions? So many architectural / data augmentation solutions have been proposed, but most tend to be very tailored to the test we proposed or specific to the task of semantic parsing and or hard to scale. So I think this leaves us, this leaves finding a satisfactory diachronic solution for the failure of this particular test I talked about an open question. And the next example I'll talk about is about entity tracking. And for kind of non-trivial, any kind of non-trivial long context understanding, linguistically expressed discourse entities need to be dynamically tracked and updated as discourse unfolds. And I just want to give you an example of a very trivial 3-sentence context. So Najoung lives with a cat. His name is Cookie. Because it's Halloween, she got him a hat with pumpkins. And understanding this context requires understanding what discourse entities exist, knowing what happened to whom, and dynamically updating the state as the discourse continues. For example, when we hear, but he kicked it back to her, we should now update the states of all 3 entities currently being tracked in discourse. So this is kind of at the interface of language capacity and like kind of the world models. And what we did was we built a test for this tracking capacity using a box world setup like the following. So there are a number of different boxes where objects can be placed in, and the changes to the locations of the objects in the world are expressed linguistically. Then the test questions are posed to evaluate whether a model can successfully track these changes in entities expressed linguistically. And one interesting observation that came out of this line of evaluation was that models that had a substantial amount of code in the pre-training data showed improved entity tracking capacity. So in this graph, you can see that the group of solid lines, which are models with lots of code in the training data, substantially outperform models without, which is the group of dotted lines. And similar improvements with code in the pre-training mixture has been observed in a series of open source model evaluation as well. You can compare the blue line versus the red line. These are actually like unpublished new results. So this test we proposed led to the finding that including a substantial amount of code in the pre-training mixture improves entity tracking. And the diachronic implication for this is that it contributes converging evidence towards the benefit of text plus code pre-training, together with a range of other work, concurrent work showing boosts on reasoning tasks. And as an aside, text plus code pre-training is kind of already customary and obviously not inspired directly by our work, but it's an illustration of how diachronic solutions can emerge from converging evidence from different tests. So I've talked about some of my work in this space, but I'd like to end with sharing some of my thoughts, takes on the design considerations for unit tests to be maximally useful for informing AI. So I think often designers of linguistic tests, myself included, don't think about this question enough, making it useful, which kind of also contributes to the widening gap in the community to some degree, in my opinion, but I'd love to hear thoughts. And my thoughts are that targets that are human-like and Okay, so design considerations for maximally useful unit tests. What do I think? So I think when utility is the prime concern, my argument is that linguistic tests should have these properties. They should be diagnostic, idealized, continuous, and to some degree paradigm and model independent. And again, I'm emphasizing here that we're not trying to use these tests to address variants of this following question: do models understand language as humans do? Then the design considerations of your tests will be very different. So I have this kind of trivial, not very like telling you much kind of diagram, but beautiful here that has a Venn diagram between human-like and useful tests, where one is important for human science, the other is important for building useful things, and they have intersections, but not completely overlapping. So in practice, you might choose to not kind of like maximize for this kind of utility considerations based on various other things that you might care about, but I'm just going to talk about utility here. So what do I mean by diagnostic? The goal of linguistic unit tests is to diagnose rather than to be optimization targets. So hyper-optimized solutions to solve unit tests are generally not supposed to be useful. So you can compare a model hyper-optimized for subject-verb agreement versus a model hyper-optimized for machine translation between a single language pair. You can see that the utility of the first is much lower than the second. It is diagnostic, not a target of optimization. And the second point is that the linguistic units should be idealized. Maybe this is the most controversial take I have today. So I argue that test cases should reflect desiderata for an ideal model, and to some degree, human level performance is irrelevant as long as we can agree on what the ideal target should be. And examples: tracking multiple entity state changes over a very, very long context has a clear answer, and depth 3 plus center embedded structures have gold parses and corresponding logical forms, although an average human might struggle with these things. And the rule of thumb I have for when we're considering whether to include hard for human test cases is, first, do we want our models to succeed on similar examples or fail, or do we not care? And second, can we actually agree on what the ideal behavior should be? So if the answers for these questions are both yes, and these are yes for both of the examples that I discussed in the previous slide, so we added them. And I also want to mention that we should actually strive to include these kind of cases in our tests because quote unquote superhuman targets are arguably more useful because we want models to do things that we can't do. And somewhat related to the previous point, ideally, test cases should cover a spectrum of difficulty ranging from easy to very hard to measure intermediate progress. For example, we have done this with our entity tracking task, dividing this up, the examples up into number of operations affecting box states, where larger might mean more difficulty. And we can see that lower number of operations get saturated from GPT 3.5, the pink line, to blue line, GPT-4, but this is not the case for a larger number of operations. And this kind of approach makes pass or fail more informative and also kind of ties back to the idealized test arguments by having kind of gradient differentiations between easier and hard cases. And this is the final point. I argue that we need to think about paradigm and model independence in designing our tests. I've kind of been deliberately shying away from using the term LLM or even LM, and instead have been using the term AI. And this is because paradigms and dominant models can shift. But on the other hand, I do think that language as an interface will stick around for a while because users of AI are humans and we use language to communicate. And insofar as this is the case, well-designed linguistic unit tests will be valuable. So kind of the point, unit tests should be designed to last longer than models and paradigms. Okay, summary, linguistic tests can serve as unit tests for models that can communicate and reason through language. The linguistic unit test can diagnose systematic failure modes that downstream task-specific benchmarks can miss. And also there are a lot of considerations for designing linguistic unit tests that are also maximally useful for AI that might actually deviate from considerations for designing tests that are useful for the science of language. And we, or like I, should also think harder about this. And thank you, that's it.